All right. Hello, everyone. Today I am going to go through our final lesson from kinematics unit, and it is just going to be one last big kind of projectile motion example that's going to cover all of the bases that we've gotten to in this unit. So we're kind of wrapping everything up by doing one question that's going to kind of touch on a whole bunch of those different concepts that we've gone through in the previous lessons. Let's just jump straight into it. From a height of 35 meters, a stone is thrown with a speed of 25 meters per second at an angle of 60 degrees above the horizontal. The stone lands on the ground. Find the time the stone was in the air and how far horizontally it traveled. And also find the speed and the direction of the travel at impact. These last several words here is something that is very, very common for students to get mistaken on. We hear impact and we hear when something stops, when it hits the ground, its impact, we think of it as stopping moving. Now, I don't want us to think about it this way. This is not the way that we think about it in physics because the object, we want to know how fast it was going when it hit the ground. Now, if you are having a hard time picturing that, consider a rock falling from the sky and you're lying right on the ground. You wouldn't want that rock to hit you at impact because it's moving with the velocity. Okay, if that rock was moving at 0 meters per second at impact, well, then you wouldn't care if the rock fell on you. But it's not its velocity at impact. Its velocity at impact is how fast it was moving when it strikes the ground. So don't think when you hear at the end there that it's going to be 0. No, it's going to be its final velocity, will be a non-zero number. So our first question is to draw a picture of the trajectory of the stone and include the information that's given in the question. And the tricky part about this question is that the stone is thrown from a height of 35 meters. So we could think of it as being on some sort of building or some sort of cliff, but the height at which we throw the stone initially is 35 meters. Now that stone gets thrown at an angle of 60 degrees. So it should look something like this. We'll do this, 60 degrees. And it said it was 25 meters per second. Now we need to draw a picture of the trajectory and we need to include the information, all the information given in the question. So I think we're good so far. We have its initial height, its initial velocity, and the angle at which it is moving. Now this stone is going to go something like this. And the tricky part about the question is that the stone, say it started right here, perfectly circular stone, is going to finish moving. It's going to make its impact on the ground. So at a different height than which it was thrown from. So there's some really key kind of aspects of this question and points that we should be paying attention to when we're looking at this question. I'll circle a few of them. Obviously, where it begins from is very important. And obviously where it ends is very important. So these are some key points to keep in mind. Another one that's very important is when it reaches its max height. When it reaches its max height, something happens to the y velocity. We've talked about this in previous lessons, so you can try to think of that. But at its max height, something interesting happens here with its y velocity. It slows down to 0 and then accelerates from 0 back down towards the ground. Now there's a new interesting point, and it's actually the point that if I just drew a dotted line the whole way across here, there is a key moment right there as well. That right here is going to be a point where the stone is going to be moving exactly 25 meters per second, not up anymore at 60 degrees, but it's going to be moving down in the opposite direction. We'll get there, but this is a really important point right here too, to be aware of. Okay. So we gave ourselves a little bit more information than we necessarily maybe needed. Keep in mind that the ground level here, this is 35 meters from this point right here as well, right? This right here, that's also 35 meters. So just some information that's actually useful for us. Now, I kept this in red. This is not it's not hating anything here. I'm just showing you that right here, this is also the same height as where it was initially released from. Okay, let's get started. So find the horizontal and vertical components of the initial velocity of the stone. This is a pretty straightforward problem here. We've got an angled velocity of 60 degrees, 25 meters per second. We're getting pretty used to being able to find the x component, Vx, and the y component, Vy. Now I don't just want to call them Vx and Vy, I want to call them V1x and V1y, okay, because this is the initial x component and the initial y component. This is a concern to us, right, because we need to consider the initial and final components of the velocity at a bunch of different points in this question. So this one, don't get too complicated. V1y, it is the opposite of the angle. So it is 25 sine, so it's the hypotenuse, sine of the degree of the angle. So 25 sine 60 degrees. And if we plug that into our calculators, we should get 21.65 meters per second. And just for this specific answer, our sig figs are 2, so we're going to round this to 22 meters per second up. 22 meters per second up. So that right there is our V1y. Don't forget your vector arrow. And our V1x is going to be the same idea, but we are now looking at the adjacent, so we use the cosine of 60 degrees. And if we do that, we should get 12.5 meters per second. I'm writing these initial numbers down because these are going to be useful as we move on. We're going to use the unrounded values so that we get a more accurate answer. And I round this one to 13 meters per second, and we'll say it's to the right. It doesn't really say what direction it's going. It's at above the horizontal. I'm just going to assume somebody looking at it from where we are looking at it from will see it going to the right. So there you go. There's part B. So we've done part B, we've done part A. Let's move on to part C. Using vertical velocities only, and that's a hint basically. It did not need to say that in the question, but it's a nice hint. That's all you need to be able to solve this problem. Find the time it takes to get to the top of the trajectory. So remember, when we're looking at projectiles, we split things into their x and y components, and we think about them only in that direction. So we think about x only in the horizontal, and we think of y. Don't get yourself all confused thinking about this. Just think about y straight up and straight down. Now we've found what v1y is equal to, and we found what v1x is equal to. And we also said, remember here, I said that at this point, if it's reaching up here, v2y is equal to 0. Vy is equal to 0 up here, but in this case, this is going to be our final velocity where it reaches. It could also be, when we're looking downwards now, we can also use it as our V1y as well for the part where it starts here now and moves its way down. We'll get there. So it can be either or. Now in this part, we need it to be our final velocity. So our initial velocity we calculated in the last question, V1y was equal to 21. I'm going to use my unrounded value to be more accurate, 21.65 meters per second up. Our V2y, we just said that something reaches its top of its trajectory, the y component of the velocity is 0. I know what else? I'm trying to find time. What else do I know? Well, we're working in the y direction, right? So we know acceleration actually. We know that gravitational acceleration is going to be 9.8 meters per second squared down. Now I've got two different directions here, so it's especially important to just take a quick moment to decide what direction we want to be positive, what direction we want to be negative. I'll make up positive, down negative. Now I know that this is a positive and this is a negative. final step is to just use the proper kinematic formula on our formula sheet. And the one that makes the most sense, we've got A, we've got delta T, we've got initial and final velocity. We're going to use V2y equals V1y plus A delta T. And I've lost my formula sheets, but that's okay because know that one from memory. There we go, I found it. Yes, that's good. That's the one we want to use. And we have V2y is a 0. So we can get rid of that right away. It's really nice. So now we have to isolate for delta t. We're trying to find delta t. So let's move our v1y to the other side first. And we'll have a delta t equals minus v1y. This is where it gets really important to be able to remember whether we're using positive or negative values. Because watch, now I'm going to have delta t. I'm going to divide by a on both sides and I get minus. Now let's plug in our values. We're going to use our scalars now. So now we're going to get rid of our vector arrows and we're going to use positive and negative numbers to represent the directions. So V1y was up, which means it was positive. I'll even put a little positive sign here. 21.65 divided by A, which was down, so a negative value. And look at that. We can see right now that our negative values are going to cancel each other out, which is awesome because whenever we're finding time, the last thing we want to get is a negative number. We do not want to get a negative number for time. Okay, so if you get in a negative number for time, chances are that you have probably mixed up a positive or a negative somewhere along the way. So doing 21.65 divided, we can even show this, the negative cancel here. 21.65 divided by 9.8, or you can do negative 21.65 divided by negative 9.8. Will both give you 2.2 seconds. Yeah. Part D. How much higher is the stone at the top of the trajectory than it was at its release? So how far did it travel in that distance or in that time that we just calculated? So we have a whole bunch of the exact same information we can use here. We still know that we're talking about that release up to its peak, right? We're still talking about, like, if this is our full trajectory, that was on the last page, we're still just looking from here to here. Okay, so a couple things here. Remember, from our last question, V1y, we already calculated it, 21.65 meters per second up. Acceleration, don't forget your vector arrows, 9.8 meters per second squared down. V2y, we said that we remembered that V2y, when it reaches its peak, is 0, right? So 0 meters per second. There's no direction involved with that because it's 0. And we are trying to find what its displacement in the y direction is. So setting up a positive and a negative direction, why don't we, just out of curiosity's sake, why don't we just decide, just because I'll show you how you can set either direction to be positive or negative, it'll still give you the same answer. Let's just do it. Let's make the negative positive and the negative positive, the downwards direction positive and the upwards direction negative. Okay, we're back. I had somebody walk into the room, so let's continue. So I was just finishing saying that we're going to make the downwards direction positive this time and the upwards direction negative. And this is strictly just to show you that as long as you're consistent throughout the question, it should not make a difference. You should still get the same answer. So let's try it out. So we have to use a different formula this time because we're trying to find delta dy. So v2y squared equals v1y squared plus 2a delta dy. Now, don't forget, vector arrow. Our life is going to get a lot easier here when we realize again that v2y squared, that's just 0. So same exact idea, moving my v1y squared to the other side, I'll get 2a delta dy equals negative v1y squared. Now don't get confused. This is all inside of here. The negative is in front because I moved it to this side. So now all that's left to do is divide by 2a, and I'll get delta dy. Now I'm getting rid of my vector arrows because I'm going to start plugging in my magnitudes, my scalar values, and I'll get v1y, which is 21.65, almost wrote a 1 instead of a 2 there, squared, don't forget the negative, over 2 times, we got a, again, remember, this is I chose to do this time to show you. Don't forget, up this time is negative, so the negative should go here, and down is positive, so I should get 9.8. Positive. Now, this is going to throw some of you for a loop here. Let's put our brackets here so it's really clear what's going on. Negative 21.65 squared should give me a positive value. Then I square that, giving me a positive. So now I've got a positive here, but then a negative in front of it. And I'll have a negative value here. Let's grab our calculator. I did it all on my calculator beforehand. So negative 21.65 squared. Okay. And then divided by 2 times 9.8. Right? We've got 23.91, but it's negative. And that's okay. That's actually okay. Because negative 23.9, well, we want our direction to be upwards. It's going up. Well, up is negative, right? So that's why I'm saying, as long as you're consistent throughout the question, it should not matter whether you decide to make it positive or negative. Your direction and your final answer should be the same. In this case, negative means up. I decided that beforehand. So 24 meters for sig figs up. All right, this is going to be an over 20-minute lesson, but that's okay. We're making progress here. We've got 3 left to go. How high is the stone above the ground? So here it said how high is the stone at the top of his, how much higher is the stone at the top of his trajectory than it was at its release? Now it says how much higher is the stone above the ground. So what we do here is we have a total height. And our total height is delta dy. We can call it maybe TOT, delta dy total. That's just the height from which it was released. And don't forget, way back at the start, we said that it was released from 35 meters. So it's 35 meters plus 23.91, another 23.91 meters up, gives us a total height of 58.91. Again, choosing to, that was a 9.1, sorry. Choosing to use my unrounded values, even though my answer here, delta dy total, is going to be 59 meters because we want to use proper sig figs. But now I have this value that I can use in my later questions so that I don't use a rounded value and I can continue to keep my answer as accurate as possible. This will be very, very important moving forward when we start to work with numbers that are either really large or really small, okay? Because the difference is the changes that it ends up making become more drastic. All right, how much time will it take for the stone to travel from the top of its trajectory to the ground? So now, if I have this trajectory drawn out again, it looks something like that, right? Now we're only concerned going from here to here. So now a whole bunch of stuff changes. Not a whole bunch, but some stuff changes. The first and most important thing that changes is that no longer are we looking at the peak of its height as being 0. We're now looking at it from starting from this position. So now our V1y value is equal to 0. So it's not V2y anymore, it's a V1y because we're starting from there. Acceleration in the y direction never changes, always 9.8 meters per second squared down. And let's go back to our regular ways of making up. Generally is positive, down is negative. Okay, and then our distance that the object is going to travel, the stone is going to travel, is delta dy, what we calculated, that total delta d that we calculated in the last question, which I'm going to use 58.91 meters. And it's starting from up here and it's falling down here. So our distance is actually also down. Do I have enough information here? Yes, I do. I have 3 pieces of information that I need, and I'm just trying to find a fourth. How much time will it take? So the formula we're going to use here is a bit of one that we use a little bit less often, but it's delta dy, and we'll continue to use the proper subscripts. Delta dy total equals v1y times delta t plus 1/2 a delta t squared. Now, immediately, v1y multiplied by delta t, that's all just 0. Okay, now let's plug in this case, because I have this delta t squared, I feel like students don't really like rearranging until we've got numbers in there. I feel like sometimes it just helps us to visualize it a little bit easier. You can do it either way, but why not right here? Let's just get it out of the way. Let's plug in our scalar values right away. Delta dy total is 58.91 meters down. So this will be negative 58.91 equals 1/2 times negative 9.8 delta t squared. So we can take negative 9.8 right now, and we can divide it by 2 because that's what 1/2 is doing. We get negative 4.9. So we should get delta t equals negative 58.91 divided by, this would just turn into 4.9. So if it was multiplied by delta t squared, now we divide it onto the other side. So negative 4.9. And if we want to find this, we just take the square root. It's the opposite of the square, right? So we take the square root, and our final answer, again, you don't want to have negative values for time, and you don't want to have negative values underneath the square root for sure. Try doing that. Won't work out. So negative 58.91 and negative 4.9, well, if we do that, we'll notice that they will cancel. The negatives will cancel. And we'll get a positive number, and then we take the square root of that positive number, and we should get 3.47 seconds. So in proper sig figs, we've got a final answer of 3.5 seconds. And so our final question after this is, how much time did the stone spend fully in the air? So now we're looking at the time it took for it to go from its release point to its peak, and then the time it took for it to get from its peak all the way to hitting the ground. So all the way to hitting the ground. All we need to do here is find 2 different values that we calculated. Delta t, we'll call it delta t. We'll do the same subscript, total. You can just do a t as well if you want a capital T underneath. But it's going to be the total time it took for it to go up and the total time it took for it to go down. We'll just add them up. So in our first part of the question, let's go back and take a look. We actually did calculate how long it would take for it to go all the way up, and it was 2.2, and more specifically was 2.21 if I hadn't rounded. So 2.21 plus 3.47. Okay, so 3.47 and 2.21, and we're using those values because we don't want to round too often. It didn't end up changing the answer really that much at all because we're going to round it to 5.3. We're going to round it to 5.7 seconds anyways. And that's it. That is our total time that it took for the ball to move from its original point up to its peak and then all the way down to the ground. Now in this question, it actually doesn't specifically ask you to calculate the final velocity of the ball, but there is some questions, there are some questions that you will see in your practice problems where you will be asked to calculate the final velocity of the object. So what you need to do is you need to find Vx. We never ended up actually having to find Vx in this question. But you'll have to find Vx, which we did have to find it. We just never had to use it again. You'll find Vx, and remember, that'll be consistent the whole way through. And then what you'll have to do is when you're doing the problems like this, now that you'll have the time that it took for it to fall, instead of finding or using V1y, find V2y. So that'll be the y component. So you've already found Vx, right? And it stays the same the whole time. And then you would have been able to find the y component of the final velocity. So this would be V2x. Is V2x, the key takeaway here is that V1x is equal to V2x, right? Because there's no deceleration or negative acceleration in the x direction. So now look, you've got this, and then your final thing that you would have to do is find, I know it doesn't really match up, my drawing's not perfect there, but is find that hypotenuse and that angle if you ever got a question that asked you that. And that R, in other words, would just be the final velocity, V2. Okay, so that would be V2. You guys have all the tools to be able to do that. Remember, this one is V1. So good luck. If you find a question like that and you're not sure what to do, you can just let us know, ask a question, email or in person. You can wait till class. But just remember to take things one step at a time and don't get overwhelmed by how many parts to a question there might be. Just do what you know. I promise once you get started, you will feel better about the question than if you just sit there and stare at it blankly. Okay, I hope this helped. Thanks for sticking with it. And your next thing to do is just do some more practice problems on this, and then you can work on your review. All right, take care.